All right, so picture this. You've just run your blast search, you're looking at the results, and you're thinking, okay, what does all this actually mean?
So, the result says 72% identity. But then you're reading a paper, and it calls the protein similar, and to top it off, your professor says they're homologous. So, are these all just different ways of saying the same thing? No way. And honestly, confusing these terms is one of the most common mistakes in bioinformatics. But don't worry, today we are going to clear this up once and for all. Okay, so the key here really boils down to one thing: knowing the difference between a measurement and a conclusion. Let's break down our terms, and we'll start with the easiest one, the measurement.
All right, sequence identity. This one is super simple. It is literally just the percentage of spots in your alignment that are an exact, perfect match. That's it. It's a straight-up number, totally objective, totally measurable. So let's say you've got two sequences. They're 100 amino acids long. You line them up, and 72 of those positions match perfectly. Boom, you've got 72% sequence identity. Yep, it's really that simple. Okay, so now let's level up to sequence similarity. This concept kind of builds on identity. It takes all those exact matches, but then it also counts what we call conservative substitutions. What does that mean? Well, it's when you have a swap between amino acids that are chemically alike. Think about swapping leucine for isoleucine. They're both hydrophobic, so it's a pretty safe or conservative change, right? And to figure out the scores for these sensible swaps, we use special tools, these substitution matrices. You've probably heard of Blossom 62, that's a really common one. So this leads to a really important rule of thumb. Because similarity counts everything, identity counts plus the similar stuff, the similarity score is always going to be the same as or higher than the identity score. It can never, ever be lower. Makes sense, right? Okay, everybody, deep breath, because this is the big one. This is where we make a huge conceptual leap. Homology, it is completely different. It is not a number. It is not a percentage. Homology is a conclusion. It's a statement about shared ancestry. It's you, as the scientist, saying, I hypothesize that these two sequences evolved from a common ancestor.
And here's the thing about homology. It's a yes or no question. Your sequences either are homologous or they are not. There's no in between. It's kind of like you can't be a little bit pregnant, right? You either are or you aren't. Same deal here. You can't have 40% homology.
And that brings us right to the single biggest, most common mistake people make with this stuff. So let's just bust this myth right here, right now. I guarantee you will hear people say, oh, these sequences are 40% homologous. Please, please do not be that person. That statement is just biologically meaningless. It's wrong. The correct way to say it is to state your evidence first. The sequences are 40% identical. And then you state your interpretation. And therefore, we infer that they are homologous. You see the difference? You use the number to support your conclusion. And look, it's not just me being picky. Here's a quote from David Mount's classic Bioinformatics textbook. He calls this out as a common error. Getting this right is absolutely critical for good science. It shows that you actually get the concepts, you know? And that's super important whether you're annotating a genome or, hey, building a phylogenetic tree. Okay, theory's great, but how does this work in the real world? How do we actually go from our identity score, our number, to making that big call about homology? Let's get practical. So this is a pretty handy guide for making that inference. If you see identity over 70%, yeah, you can be pretty confident they're homologous. Now, if you're in that middle ground, say 30 to 70%, homology is likely, but you should probably look for some other clues, like similar protein structures or functions, just to be safe. But then, below 30%, welcome to what we call the twilight zone. In this zone, the sequences might be homologous, but the signal is just too weak to be sure from the sequence alone. And that, my friends, can be a real headache for evolutionary research. All right, let's bring it all home. If you only take away one thing from all this, make it this next part. This is your bite-size breakdown. Okay, number 1, identity. That's just your exact matches. It's a percentage. Number 2, similarity. That's your identity plus those conservative, chemically similar substitutions, also a percentage. And finally, number 3, homology. That's the big evolutionary conclusion you make based on the data. It is not a percentage. So let's say it one more time, loud and clear. Identity and similarity. Those are your numbers. That's your evidence. Homology, that is your conclusion, your interpretation of that evidence. Do not mix them up. And really, that's the whole shebang. Nailing this distinction is going to make your work so much stronger and more professional. I mean, this stuff matters for everything, from figuring out what a new protein does all the way to mapping the entire tree of life. Hey, thanks so much for joining me. Make sure you hit subscribe, because next time we're going to take all this and actually build a phylogenetic tree. You don't want to miss it. See you on BioinfoBytes.